This is the work of the Tesla AI team over the last several months, so I'm talking on their behalf here. I'd like to start with some of the recent accomplishments that the team has achieved. Earlier this year, around June, July, we launched our Robotaxi service, where if someone was in Austin or in the SF Bay Area, they can hail a Robotaxi service from Tesla. And then in Austin, below 40 miles per hour, you can get a car without anyone inside the passenger seat. So it is just driving using these cameras and neural networks. We also did this thing where we delivered the first customer purchasable vehicle from the Tesla factory in Austin directly to a customer's home somewhere else in Austin. And we covered over 20, 30 minutes of driving across highways, city roads, parking lots, etc. to deliver the car. You can see the car driving itself. And this is a production vehicle out of the factory using production cameras, the same computer that's in every car and so on. Every Tesla that's manufactured in the US also delivers itself from the manufacturing line all the way to the loading docks. That's like a couple miles away. So this year we made a lot of strides in autonomy, and we continue to scale the technology to be even more robust and resilient so that we can go to more locations, have no one inside the car, and so on. Today I'd like to touch on some of the technologies that help power this self-driving. So first of all, we switched to having a single large end-to-end neural network that can take in pixels and other sensor data as an input and then just produce the next action as an output. So while it's driving the car, it no longer is doing explicit perception of vehicles, road boundaries, or things like those. They can be implicit and they can be trained as auxiliary things, but then the entire thing, the raw video streams go in, and then the actual actions to take are produced by the neural network. And it's been so for the last few years, and this has been extremely good. The reason being, we used to work on an explicit modular approach because it was so much easier to debug and so on. But what we found out was that codifying human values is really difficult. For example, you could, in order to brake for an obstacle or go around, you could go as fast as possible and then brake a bit later or brake earlier for more smooth driving. And this really comes down to an alignment of preference to human values as opposed to this one objective value of how much braking and when to apply. You don't want to brake too early either because then it'll be too slow. And if you don't want to brake too late either, then it's too uncomfortable. And this varies from situation to situation. The amount at low speeds or high speeds is very different. So it's really hard to codify what humans actually want. And you can't write it in code. And also the interface between traditional perception and planning is very ill-defined. It can be very lossy and lose critical information where you might need to propagate the uncertainties through the entire system. That's really hard. Going to end-to-end neural network also allows for your compute to be homogeneous. If you have traditional branching compute, you can have non-deterministic amounts of latencies. In a real-time system, you don't want to have the kind of latencies. You want to have predictable deterministic latencies, and such a single neural network doing the entire thing offers that. Overall, this is what we believe as the right path to solving robotics as opposed to this kind of modular brittle systems that were developed earlier. I have to give a few examples of why this is hard. For example, this vehicle is driving on a bidirectional road. To avoid this puddle, you got to go to the oncoming side. If you had to write this using explicit cost functions, it's going to be really hard because typically you don't want to go into the oncoming side. But then what is the pain of driving through a puddle versus the risk of going through an oncoming lane is hard to write in explicit code. But here, if you look at the scene, it's pretty obvious that you can go here. You have a lot of visibility. There's no oncoming vehicle coming, and you should definitely go into the oncoming side. It's also hard to understand intent. For example, here on the left side, there's a bunch of chicken crossing the road. I'm not sure if the video is clear for you guys, but there's a bunch of chicken crossing the road. This is driving on self-driving software. And it's just waiting for the last chicken to cross here. And then the car proceeds on its own. This is all just driving on its own. In this case, the car was smart enough to understand that the chicken actually out crossing the road and was patient enough, even though there was no collision risk. It was just the right thing to do. But in other cases...
Look, it's going around him. It's going around him. Oh, look, it's changing its mind. It's backing up to go around him. Look at that. It backed up to go around the geese.
In this case, the model understands that the geese are actually not crossing, they're just stationary and decide to reverse and then go around them. So it's not, this is something that it's very hard to write in explicit code, what is the right thing to do here. But looking at the scene end to end, and for humans too, it's pretty obvious what was the right thing. And that is why end to end is way better than a modular approach. That said, it's not that easy to develop such a system. It's pretty difficult, in fact. And I'd like to touch on 3 different aspects of it that make it really difficult. First is the curse of dimensionality. What I mean by that is that the input context in this quite enormous, especially our cars have 7 or 8 cameras depending on the vehicle. Each produces 5 megapixel camera streams running at like high frame rate. And even if you want to have 30-second context or something like that, along with the other necessary inputs like the routes and then the vehicle speed and other kinematic data, it can easily be more than billions of tokens, like 2 billion tokens for a 30-second context window. And if you natively just use some kind of transformer, it's just going to be really difficult task of mapping 2 billion tokens down to roughly 2 tokens, which is what is the next steering and acceleration that the car should take. Thankfully, Tesla has a huge advantage here, which is the Tesla fleet is quite large. So it's basically has access to the Niagara Falls of data. And it's up to Tesla to use this data to solve this problem. You don't want spurious correlations from the 2 billion tokens down to the 2 tokens. You want the right correlations as to why those 2 output tokens must be the right tokens. So what we do is we refine this 500 years of driving, which obviously is more data than we could ever store on our clusters, to the essential amount of data, which covers the overall spectrum of driving. There's different ways we can collect this data based on like explicit triggers or small neural networks targeting specific scenarios, constantly evaluating what the model predicted versus what actually happened, and things like those. We can use such tricks to extract just the right amount of data, the right quality and the kind of data that we need for our training. Here's some examples of what that kind of corner case data might look like. These are examples in manual driving, like people are just still driving and then they encounter such rare scenarios. We can have triggers that cache these. This is very useful data to train on, and this is not normally accessible. You can't stage this that easily because it requires the stationary scene, the speed of all the vehicles in state space. This is really hard to achieve. And Tesla has a unique advantage here that it can tap into the entire fleet to get this data. Once we get this data, you can use this to train our end-to-end model, like I mentioned before. And it just generalizes to extreme scenarios like these ones and not just reacting at the last second, but proactively safe. I'd like to show a demonstration of like how that manifests. Like this is, again, a self-driving system in operation here, just on a highway. Here, the car in front of us spun out and then hit the barrier, and the self-driving system pulled over safely. But what is quite interesting is that if you watch the video again, I like pause where the ego car brakes. Like here, if you notice this car here, it's like spinning out of control and it's going to hit the barrier and it's going to bounce back into a lane. It requires so much intelligence to know that this is not a first order collision here, because at this frame, the Tesla already determined that this vehicle, there's something wrong here and started applying the brakes. It did not wait for the car to hit the barrier and then bounce for its velocity change or something like that. This is a second order effect that needs to model. It could have also attributed this to a lane change of this vehicle, but it did not. It understood because it was requesting roughly 4 meters per second square of braking, which is not a light amount of braking. This is only possible if you have a ton of data and cover all these corner cases. That is how you can provide both safe and also a smooth ride, because a less intelligent system would wait until the direction has changed or actually some bad event has happened way before it actually goes wrong. That is what you get with an end-to-end system with a ton of data. Secondly, so if it's an end-to-end system, how do you guys debug? How do you actually develop this thing? If something goes wrong, how would you know? Just because it's an end-to-end system does not mean that it cannot predict anything else. The same model can be prompted to predict arbitrary things, including occupancy, other objects, traffic lights, traffic signs, road boundaries. Even just in plain language, you can ask it why it made some decisions, does it understand the scene, and so on. All of this helps interpret the model's understanding and also sort of like give some guarantees around the safety of the entire system. So in practice, it sort of looks like this, where you can take in arbitrary sensor data and prompt it to produce arbitrary things. But in the end, the only thing that actually matters in the car is the control actions that it produces. Everything else is auxiliary, but they can be quite helpful for predicting the correct control action. One specific task that I would like to go over is the Gaussian splatting, which in the last few years has been quite prominent in the field. But what I'm showing here on the left side is the traditional Gaussian splatting. The problem typically is that vehicles drive in sort of a linear fashion going forward, and there's not a ton of baseline. Because of this, if you just took the same camera views of the vehicle's motion and ran traditional Gaussian splatting, Nerve Studio or what have you, with the same camera views, the views close to the train views look great. But then if you go to novel views that are far away from the train views, it breaks down quite a bit. But what we have in the middle column here is Tesla's variant of Gaussian splatting, where the same model can produce Gaussian. It generally is much better with the same limited camera views that the left side has. It can also produce semantics as shown in the third column. And the cool thing is that it can run ridiculously fast compared to traditional Gaussian splatting, which can take tens of minutes. So you can see that this can update to scenes quite rapidly. If you use the same traditional splatting, a lot of novel views might look blurry or like fuzzed out. But as I'm rotating here in 3D space, a lot of the structure remains intact. And such interpretable representations can be used to debug the system. Like if it's going faster or slower, you can easily observe, okay, is it safely avoiding some obstacle or not? Like I mentioned earlier, we can also use natural language to interact with the model. The same model can sort of like point to things, explain why it made some decision. We shouldn't need all of this to drive the car in real time, but then if you do need it, you can always think longer and produce reasoning tokens to then produce the right action that is consistent with the reasoning of the entire thing. And again, it can be the same model that's running in the car, but based on the situation, can use it or can directly produce the control actions if it's not required to reason in such detail. Because if you keep reasoning in detail for every single thing, then it's going to take too much latency. But then wherever it's needed, it could reason longer to produce the right answer. The last piece that I'd like to touch on is the evaluation, which actually is the most difficult of these three problems I mentioned. If you just train a bunch of data from drivers and then train the models and just like scale it, your open loop performance like look amazing, but then it may not translate well to how the car actually drives. A lot of reasons for this. I don't want to get into the details there, but then it is a very important problem that requires a lot of attention to get good performance out of the system. Evaluation sets, it's not just, if you randomly sample data from your fleet, most of it is going to be boring highway driving. You don't want to just be evaluating there. That's where the early data engine approach that I mentioned comes in handy, where we can build a balanced, fully covered eval set, which is extremely important, but very tedious work. One great thing we figured out was that we can use the cheap to collect state action pairs, invert it, and then basically build a world simulator where given past state and then actions, it can synthesize newer states, this condition on the actions. This is quite easy to collect because you can get it for free. You don't need optimal driving or something that any kind of trash driving is good enough for this kind of simulator because it needs to simulate the edge cases. Then once you have that, you can connect that with our policy neural network that's driving the car, and then they can both run in sequence in a loop to sort of simulate the world. Here's an example of our rollout through learned neural network simulator. I'll let you watch the video for a second here, but the entire thing is generated video. There's 8 cameras. The top row is all the front cameras of the car driving forward. The middle ones are the left and right side cameras, and the bottom row is the rear-facing cameras. All 8 cameras are generated simultaneously by a single neural network and takes action as an input, so you can steer the network. I'll show you in the next couple of slides how that can work. I'm usually blown away by the consistency of generation across different cameras. Even the vehicle rims are consistent. The traffic lights, this is over like a minute and a half long generation of 8 5-megapixel video streams. In addition, you can take like past issues, like take a year-old issue, and then you can rerun the latest neural networks to see how they would perform. On the left side here was the original failure, where it was maybe a bit too close to the pedestrian. And then on the right side, we are evaluating a newer neural network that's driving the car. You can see that the policy starts offsetting way earlier as soon as the pedestrian emerges from behind the car. It's super useful for such kind of evaluation because you don't want to just re-evaluate on newer mileage. You just want to, if you have a database of older issues, you just want to replay them and verify that you are doing a good job on this past issue. You can also synthetically create new issues. In this case, the original video on the left side, that vehicle was just going forward in its own lane. But then on the right side, we can make condition the vehicle to cut across our path and then inject this kind of adversarial event to test the system's corner cases. And you can see that the scene and the rest of the scene remains consistent. All the other vehicles are moving the same way. It's just that this one vehicle cuts across. And that's how you can make lots of synthetic data sets to verify the corner case performance of a self-driving system. If you are fine with reducing the test time compute a little bit, you can get close to real-time rendering performance. This is the same model that's rendering the 8 cameras with lowered test time compute And you can see that you can actually drive this in real time. The FPS is high enough, even though it's generating 8 5-megapixel streams in parallel. So obviously you can see that it's responding to the user's driving commands. They can steer and brake and then navigate the world just as if they're driving in the real world. But the entire thing is neural network generated video streams. I think the driver is trying to do something adversarial by going on the curb and then just demonstrating that the generalization of the simulator is quite good. Yeah, this entire video is 6 minutes long, and you can just have consistent video generation for a very long time and responding to controlled commands. You can hence imagine like how this tool can be quite powerful, both for evaluation purposes, but also for closed loop reinforcement learning, where you can just let the car drive and then verify that it doesn't collide with anything for a very long time. So yeah, what's next? We want to scale the service to be much, much better and then unlock the entire fleet of Tesla vehicles to be fully autonomous. This is the Cybercab, which is our next-gen vehicle, which only has like 2 seats and designed for the purpose of robotaxi. It's going to have the lowest cost of transportation across even public transportation. And it's all powered by the same neural networks that you saw earlier. We find that the approach that we took is quite scalable. It scales across different vehicle platforms, different spatial locations, different weather conditions, and overall offers a very safe, comfortable, and fast ride to the users. There's one more thing, which is it's not just scaling self-driving to all the vehicles, but also scaling it to other forms of robots, the humanoid robots too. Tesla builds humanoid robots. We call them Optimus. And the same technology that we developed here for self-driving transfers most seamlessly to other forms of robots. I'd like to show one example here, like the video generation also works for Optimus. So this is Optimus navigating around the Tesla factory, and all of these are generated videos. And you can see that they are all quite consistent. You can also, just like how we did for the car, action condition it. So here, the top left is the robot just going straight. That was the ground truth. But then you can have different actions like going left or right or some other direction, and then it can correctly generate the pixels for the action. So yeah. In conclusion, Tesla is all in on robotics. The entire company is just focused on producing intelligent, useful, large-scale robots for helping everyone in the world. And if you are working on AI, robotics, computer vision, etc., encourage working at Tesla because it has like extreme real-world impact. It's fully in on solving robotics. The team is super pumped. I think it's a great place, and it's the best place to work on AI right now. Thank you.
So we can have questions. By the way, Ashok, you can see the room actually. So we have shared the screen, so you can see the whole audience.
Thank you.
Thank you also for your interesting presentation. I have a question about the end-to-end paradigm. What we see an end-to-end system that's solving at a some level of modularity, either implicitly or explicitly. For instance, different input sensors require different encoders because different sensor models require different types of attention, spatial attention, or causal attention. So in your view, do we still need these sensor-specific only, and if you have enough data, everything can be handled by the same transformer?
Yes, the sensor-specific encoder could still be more efficient, but I would say it's an empirical answer. You just try out different encoders, whatever works best, you use it. But you do need to keep in mind the real-time considerations. We just naively use a large transformer for this purpose. Like I mentioned, there's a lot of input tokens. It could be like billions of input tokens. If you just naively patchify it and use it, you're going to run into compute struggles and you're not going to meet your real-time latency requirements. So, for latency considerations.
But interpret your market answer is that is some level modularity still in the Tesla approach because there are sensor-specific ways of tokenizing the data.
Because the end-to-end is not conflicting with the sensor-specific ways of tokenizing things. The only requirement is that the gradients flow all the way.
Hello, thanks for the couple of questions. Which does not the foundations, the evaluations, the hardest. You showed some work differently, word models, we should be simulate and sensitive. So one question I have is, if you want this word model, what else can you produce from that word model neural network, which will allow you to evaluate quantitatively? For example, real data, you go and you just label it in the ground, so then they use that to modeling how accurate is my flow, how accurate is my estimate of the trajectory of the adversary that but in the loop, which is inserting that knowledge. Right? So that property that water bottles, is there a danger that when you start modeling the water bottle replaces one, and then you can't really tell. It's funny.
I mean, even if it's closed loop, you still have a knowledge of how the scene evolves. So you could always verify it against any kind of objective metrics around, for example, collisions or how much jerk or whatever parameter that you have used for your controls. So that's not conflicting. The only downside I would say of using closed loop is that it's quite expensive. You know, make sure that you use the right tool for the right thing that you're measuring. Something is for perception, for example, even though it's an end-to-end system, like I mentioned, you can obviously have intermediate outputs and you can measure perception using open loop way because your prediction that does not affect the scenario as much. But then for action, your prediction there affects the environment quite a bit. So that's where it becomes tricky to just depend on open loop evaluation.
Thank you. Hi, thank you for the nice presentation. I have a question for you. The first question is that you showed some validation model for Optimus driving, but do you still maintain the session and the letting like the modules and still use the vector space representation for your Optimus driving? And B2B Optimus space. And the second question is that it seems the audio model seems to be acceleration and steering, but do you use the trajectory, the waypoint for your planning, and then convert that into the acceleration, the steering, or that is the direct output of the AI model?
Yeah, I don't want to get into the specifics of the exact architecture, but the main premise of end-to-end is that the gradients must flow end-to-end. As long as that is true, you can have auxiliary outputs, not have them. You can predict steering, curvature, or predict other trajectories. As long as the only requirement is that the gradient must flow end-to-end. So the learning, like every bit of information that's flowing in from the sensors gets used for the decision making. That's the only premise. Everything else is an empirical question of you can do different things and see what works best and then pick that one for your setting. Some people prefer some output space, other people prefer something else. But I would say that's sort of, in the grand scheme of things, a no-op in terms of like what actually matters. That doesn't matter as much.
Thank you. Do we have any other questions? If not, let's give a huge round of applause to Ashok. Thank you for coming in.
Thank you. Thank you for listening to me talk.
Thank you. So we are going to continue with our next speaker, Jamie Shotul. Jamie is based science department where he guides the research teams to unlock new research breakthrough to enable those breakthrough to have meaningful impact for business and to disrupt both technical and the business strategy to ensure Wave stays at the forefront of innovation. Jamie had been at the forefront of applied research for the past 20 years. Before joining Wave, Jamie was partner director of science at Microsoft and head of the mixed reality and AI labs. While at Microsoft, Jamie shaped foundational feature for Microsoft line of motion sensing and input devices, and the hand and eye tracking that enable HoloLens to interaction model. Jamie had a PhD in computer vision from the University of Cambridge and had received multiple best paper and best demo awards at top-tier academic conferences. He was elected fellow of the Royal Academy of Engineering in 2021. That's that from the Jamie for the talk. Thank you.
Okay.
All good. Yeah, from me.
Okay, we've got the right thing there. We've got audio. Hopefully, you've got a camera. Okay, awesome. Let's go. Good. I think it's still morning. So good morning, everyone. Great to be here. Thanks for organizing this fantastic workshop and amazing set of speakers. So I'm Jamie. I'm from Wave, and I lead our research team, among many other things. And I'm going to be talking a little bit about Wave and where we are and where we're going, and a few little sort of research snippets as well towards the end. Well, unfortunately for most of us, the reality of driving looks much more like this on a day-to-day basis. And in fact, the average North American driver spends 2 full days of their lives each year stuck in traffic. Wouldn't it be amazing if we could get that time back to read, to play with our kids, to work? Well, seriously, there is a huge toll we pay as a society for our use of the roads and our mobility. Statistics from the WHO here. And the sad fact is that the majority of those accidents are caused by human error. These are things that machines shouldn't fail at. And so I'm far from the first person to have asked the question, wouldn't it be great if cars could drive themselves? And for these reasons, plus the potential huge economic possibilities of this, self-driving has become the space race of our generation. And we've seen just a few of the companies in this space already this morning talking here on the stage. But despite progress, we still see almost daily headlines like this appearing in news outlets. Some of this is unfair, absolutely. And, usual media hysteria to plug holes at things. But equally, it's very true that autonomy is not yet everywhere. We've seen great examples of Waymo. They've done an amazing job at deploying robo-taxis, but they're in a very small handful of cities around North America at the moment. We just saw Tesla, and they've done a phenomenal job with self-driving. You'll come back to that in a second. But Tesla only sells 2% of the world's automobiles. How do we get this to be truly ubiquitous? And that's what we're working on at Way. What does this mean? Well, it means wherever you go, any city around the world, this should just work. Whatever vehicle you're in, it should have autonomy built in. And ultimately, it's not just about cars and automotive, but it's about all of these other forms of autonomy and robotics that could transform how we work as a society. So a little history lesson. We've heard a little bit very into this over the course of the morning, but here's my take. So after the DARPA grand challenges in the 2000s, people started to wake up to the possibility that self-driving might be a reality. And that was further accelerated by the advent of ImageNet and all of the excitement of CommNet in the 2012s and beyond. And that's led to some of the early investments in this space. But they took a very reasonable approach, you'd think, as an engineer. Let's throw some sensors at this. Let's throw a bunch of computer vision perception algorithms at the problem, recognize the pedestrians and the cars and other things. And let's use maps, right? We know now how to map out cities to centimeter level detail and to localize ourselves against those. And then once we've got all of that information, great. Let's then feed that into a hand design set of rules, or more lately, a learned set of rules for planning and prediction. And then that actually is the vehicle. And this can be made to work. That is patently obvious now. We have real deployments on the road of this today. But it has proven really slow and expensive to scale for all of the reasons that I've got up here and more. And so we've seen a pivot from at least some companies towards an alternative that I'll be talking about next. Now, while all of that was happening in the world of AV, in the world of AI, there were all sorts of exciting advances. Here's just a few, and I've given up updating this slide because it moves too fast. There was a huge sway of new developments over the last decade and a half. The foundations of modern AI, things like the data sets and benchmarks, self-supervised learning, foundation models, scalable compute architectures, multi